Welcome back to the review of my channel, my_exe. Today we're going to look at more number pattern and sequences example problems, and some of these may be a bit difficult because I've upscaled the difficulty. So anyways, this is question 1. The following shows the first 3 diagrams of a square pattern. As you can see, there are 2 types of squares. There are unshaded squares and there are also shaded squares. For the fourth pattern, if you notice the pattern, you add 2 unshaded squares on the right. I'll just demonstrate for you. So let's see. So this is the original third pattern that has 6 shaded squares, and if you notice that every pattern you add 2 shaded squares to the right, and afterwards round that with unshaded squares like so. So this is this is the fourth pattern right here. So that's part A. For part B, the following shows the information of the square patterns tabulated. So we have the pattern and then the number of shaded squares and the number of unshaded squares. We need to complete the table above for patterns 1 to 4. And that's pretty simple. We can just look at each diagram and then just observe how many squares there are each. Or I should have said how many shaded squares and how many unshaded squares. So I'll just speed up this for you guys. Alright, so that's it for the table part. And for the second part of part B, we need to generate a formula in terms of n for Tn, which is the number of shaded squares in pattern n, and U of n, which is the number of unshaded squares in pattern n. So if you notice the numbers right here for the shaded squares, this forms an arithmetic sequence because the differences are common. And if you just work that out, you'll end up that the formula for T of n will be just 2 times n. Likewise, for U of n, it is also in fact an arithmetic sequence because their differences are equal and constant. And if you work the formula out, you get that this the formula will be 2n plus 8. Alright, that's part B done. Now for part C, we're going to use these formulas to compute the following. The cave pattern has 2020 shaded squares, and what that means is we can just form an equation that T of k, this is the number of shaded squares in pattern K, is equal to 2020. Using this formula right here, you get this will be equal to 2k equals 2020, which means k is 1010. This is the first part. The second part, let's see. Find the number of unshaded squares in pattern 1001. Alright, so that will be U of 1001, and using this formula, you get 2 times 1001 plus 8, which will be 2002 plus 8, which will be 2010. And for the third part, is it possible to have a pattern that has an equal number of shaded and unshaded squares? If yes, find the order of the pattern. So from here, we can just form an equation that satisfies that Tn is equal to Un, which means the same pattern has the same number of shaded and unshaded squares. So using both formulas above here, you'll get that it will be a linear equation in terms of n, like so. However, this in fact does not have any solutions, because if you subtract 2n on both sides, you end up with a contradiction that 0 is equal to 8, which is in fact not true. So what that this tells us? It tells us that it is impossible to have an equal amount of shaded and unshaded squares. So no. So that's the first question. Now the second question will involve the Fibonacci sequence. So here's question 2. So just a bit of information. In the Fibonacci sequence, you get the value of a term by adding the two previous terms. So that is very special to answer these following. So for part A, the fourth and sixth terms of a Fibonacci sequence are 7 and 20 respectively. Find the first term of the sequence. Alright. And perhaps the way I would do it is to write a incomplete sequence and just replacing the blanks with our given information. So in this case, the fourth term will be 7. The fifth term is currently unknown. And the sixth term will be 20. And then you can just ... And due to the behavior of the terms in the Fibonacci sequence, we know that the fifth term will automatically be 13. Because to get 20, you add 7 with 13. And from here, you can just do backwards to find the first term, like so. So the third term will be 4, because to get 13, you add 4 and 7. Likewise, the second term will be 3, because to get 7, you add 3 and 4. And for the first term, which is our wanted answer, is 1, because to get 4, you add 1 and 3. So our answer in this case is 1. Now for part B, it's a bit challenging. However, if you know the trick, it will be very easy. It will be pretty easy. So yeah. So leave the first four terms blank and replace the blanks with our given information. So the fifth term will be 9. The sixth and seventh terms are currently unknown. And the eighth term will be 29. Well, we can't necessarily do the same trick as we did in the first part. However, we can just suppose some variables. Let the sixth and seventh terms of the sequence be a and b respectively. And from here, you can just build some equations regarding a and b. The first one will be b is equal to 9 plus a, due to the behavior of the terms in a Fibonacci sequence. So to get b, you add 9 plus a. Likewise, to get 29, you add a and b. So that is also another equation to consider, which is here. I'll just name this equation 1. I'll name this equation 2. So we have two systems of linear equation in two variables, which well, there's pretty a simple trick here, because notice that we have b here and then we have b expressed in a. So we can just substitute equation 1 into equation 2 to get that a plus 9 plus a equals 29. This simplifies to 2a is equal to 20. That means a is 10. Substituting back into this equation, you get that b is 19. So with this in mind, we can just replace these with our given found values here. And what is the question asking? The ninth term. So it will be the term after this. And that is pretty simple. You just add 19 with 29. So the answer in this case will be 48. There you go. So that is the second question. Alright, so let's jump into the third one. Alright, for question 3, this is the last one and it's pretty tricky. So yeah. So consider the following pattern. So as you can see, just observe it by yourself. And then we need to write down line n. So perhaps we can just find some correspondence in numbers with the term order. So let's see. So we know that this one corresponds to this one, and this two corresponds to this two, and then so on. And therefore, if we're given line n, that means the numerator of the first fraction will be still 1, and then the bottom part will be n. And I will just perhaps write this in a more neat way. There we go. And then notice that these numbers are 2 above the term order. So the numerator of the second fraction will still be the same, except the denominator will be n plus 2. And this is equal to 2 over the product of the denominators. So there we go. And for part B, we need to simplify 1 over 100 minus 1 over 102 as a single fraction. And here in this case, this is one of the members of the pattern listed here. And in this case, if you look at these terms and these terms, and then you know that this term right here will have n being equal to 100. So from here we can just substitute n equals 100 to this, and that will be 2 over 100 times 102, which will be 1 over 5,100. Let's see if I got it right. Yep, that is it. So the answer for this will be 1 over 5,100. So for part C, write down a solution for natural numbers x and y such that this satisfies this. So I have 1 over x minus 1 over y equals 1 over 1,300. And perhaps I'll just rewrite this fraction a little bit differently, just to keep this equal to this format right there. And perhaps we can just rewrite 2,600 as a product of a number times 2 more of its number. And the right combination of two numbers that satisfies this product will be 50 and 52. And just doing this backwards and using this formula for the line of n, for the line of n right here. So notice we've arrived at this format, and this is equal to this format right there. So this is also equal to 1 over 50 minus 1 over 52. And if you look at the left hand side and the right hand side, you'll know that x must be 50 and y must be 52. There we go. So that is the answer for part C. For part D, find the sum bill without a calculator and express your answer as a single fraction. So we're given this insane sum right here, and we're also given some additional terms. We have 1 plus 2,019 plus 1 1 plus 2020. Alright, so notice that these numbers are actually members of our given line pattern above here. So notice that we have 2 over 3, 2 over 8, 2 over 15, and 2 over 24. Those are exactly the same as this. So perhaps we can just exploit our given formula, and let's see what we have. So using our formula above that we have gotten for the line of n, you will get 1 over 1 minus 1 over 3 plus, I'll just put the outer brackets in such right there. So I have 1 over 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5 plus 1 over 4 minus 1 over 6, and then so on, and we'll stop until 1 over 2018 minus 1 over 2020, again using the formula that we've gotten above. And don't forget the additional terms. Alright, so let's see. We can perhaps group these into a single bracket, since we know addition is associative. So that will be 1 over 1 minus 1 over 3 plus 1 over 3 minus 1 over 5 plus so on, and we'll stop until 1 over 2017 minus 1 over 2019. And notice this grouping will only be included by odd denominators. As you can see, all of these numbers are odd, and you see why later. And don't forget, we can also group the other terms, which are the even denominators, as such. So we have 1 over 2 minus 1 over 4 plus 1 over 4 minus 1 over 6 plus so on, plus, and we'll stop at 1 over 2018 minus 1 over 2020. Alright, so notice if you remove these brackets, since we don't really care, because well, we know we can just remove the brackets if it is addition. And you can see that some cancellations are going on right here. So we have this minus 1 over 3 cancels with this 1 over 3, and this negative 1 over 5 is going to be eliminated with whatever this thing here, and whatever this thing here we cancel with 1 over 2017, leaving us with only 1 minus 1 over 2019. And I forgot to write the additional terms. Just a moment right there. So likewise, we can just do the same here. We can just cancel this and cancel this, cancel this and cancel the whole thing in dots, and then this whole thing in dots will cancel with 1 over 2018, leaving us with the first part being 1 minus 1 over 2019 plus 1 over 2 minus 1 over 2020. And perhaps we don't really need these brackets anymore. And we have the additional terms 1 over 2019 plus 1 over 2020. And again, there's one last cancellations going on here. So if this minus 1 over 2019 will cancel with this. This minus 1 over 2020 will cancel with this, leaving us with our final answer of 1 plus 1 over 2, which is 3 halves or 1.5. So this extreme sum has been done. And that concludes this video. So hopefully you guys enjoy this. This is an upscale difficulty of my usual number pattern and sequences videos. And yeah, let me know if you guys want more harder problems like so. And anyways, I'll see you guys in the next video. Goodbye.